Thank you very much for the kind introduction. So yes, I will speak for the next minutes on the applications of EURO-CORDEX data to the ski tourism sector. And this is basically and mostly drawn from a work that we've carried out a few years ago now, a couple of years ago, in the context of a Copernicus Climate Change Services, Sectoral Information Services, or Sectoral Information Systems contract. So if you move to the next slide, please. Yes. So we all understand that mountain tourism or winter tourism or ski tourism, often the three are combined, are extremely high climate sensitive because it depends on snow in the mountain regions. And we know that snow is a very sensitive variable when it comes to temperature, because under a warmer temperature, at low elevation in particular, we expect and we observe more and more rain and less snow, and then the snow melts quicker when the conditions are warmer. So we know that on the long term, in the long term, climate change has an impact on the snow cover, but also in the short term, we know that snow falls on a very discrete manner for different events during a given winter season, and this really shapes the way that ski tourism develops over the course of a winter season. So this presentation is timely in the sense that it was still in winter almost, and in an usual year, ski resorts would still be open throughout Europe at the time of we speak. And it's also a bit untimely because, as we alluded to in a minute, many ski resorts are actually closed due to the COVID-19 pandemic and its impact. And so we have to take into account not only that climate, but also other factors or have an impact on tourism and ski tourism in particular. And so for many decades now, ski resorts are not only relying on natural snow and natural snowfall, but they also managing that resource. And managing that resource is taking place in the form of grooming the snow, using grooming machines to compact the snow and to make it less prone to erosion and to moving around in ski resorts, but also producing snow when, in particular, originally when snowfall was sometimes lacking, and this has always occurred more or less frequently in the past. So snowmaking or machine-made snow production is something that has started in the 60s and 70s, but really picked up in the 90s, and now it's quite standard in many ski resorts European-wide. And when we account for the impact of climate change on ski tourism, we need to account for those practices in terms of snow management, and I'll come back to it in a minute. So if you go to next slide, please. I will start with a few statements from the summary for policymakers of the IPCC report on the ocean and cryosphere in a changing climate that was released in September 2019. And if we start from natural snow conditions, and if we extract the bullet points and the paragraphs that refer to it, we assessed in this report that in nearly all high mountain areas, the depth, extent, and duration of the snow cover have declined over recent decades, especially at lower elevation. That is, at the elevation range where the temperature has a strong impact on turning precipitation from rain from snow to rain under warmer conditions. So of course, if you're in high elevation in the mountains at the core of the winter, usually it's sufficiently cold that even on a warmer climate, precipitation remains in the form of snowfall. But as you go lower, you're more and more sensitive to temperature rise because you're looking at elevation ranges where the transition from snow to rain can occur only for slight temperature changes. And that's why the decline is observed mostly at lower to mid elevation, and it's not so clear if you go higher up, way above the snow line and the mean snow line elevation. The trends are way smaller and sometimes not detectable in terms of the core of the winter. The melt is quicker almost everywhere in the springtime, but the springtime is not so relevant for ski tourism in most cases. In terms of projections, in high mountain areas, there are decreases in low elevation mean winter snow depth compared to a reference period at the end of the 20th century, likely on the order of 10 to 40% by the mid-century, regardless of the emission scenarios. And for the end of the century, the decrease is about the same for RCP 2.6 and quite dramatic for RCP 8.5, just to give the range of the conditions that were assessed in that particular report. So next slide, please. So if we now turn to ski tourism and mountain tourism in general, we have assessed that high mountain aesthetic and cultural aspects have been negatively impacted by glacier and snow cover decline in a number of regions on Earth, and tourism and recreation, including ski and glacier tourism, have negatively been impacted in many mountain regions. And in some places, artificial snowmaking has reduced negative impacts on ski tourism because, again, snowmaking is here to compensate to the variability in snow conditions. And of course, when snowmaking is in place, in many cases, it actually reduces the variability of the snow conditions and thus the hazard to the exploitation of ski resorts. So if you go to the next slide, that's for the past, and this is for the future. And we assessed in that report that high mountain tourism, recreation, and cultural assets are projected to be negatively affected by future cryospheric changes. Again, with a decline in snow cover in the highest change in highest rate of change of the climate. This would have negative consequences for snow conditions. And also the fact that current snowmaking technology are projected to be less effective in producing risks to ski tourism in a warmer climate in most parts of Europe, North America and Japan, which are the main ski tourism markets, in particular at 2 degrees global warming and beyond. Because snowmaking requires that the temperature is sufficiently cold, sufficiently low. And so if the temperature rises too much, not only snow conditions decline in terms of natural snowfall, but also it becomes too warm to even produce the snow. And so you cannot compensate anymore by producing snow if the temperature is too high. But at the moment, there haven't been pan-European assessments of the impact of climate change on ski tourism in a homogeneous way throughout all the mountain ranges of Europe. And that is exactly what we've done through that contract, which now led to data available on the climate data store. So if you go to the next slide. So for assessing the impact of climate change on ski tourism, we need to account for to the processes that occur in a snow cover, combining the processes that take place in the snow cover naturally, so all the precipitation terms, snow and rain precipitation, but also the transformations within the snowpack and the energy balance of the snowpack and the interaction with the underlying ground. And we developed and used in that work a specific version of the snow cover model Crocus, that has been developed for many decades now, and is primarily used for supporting avalanche forecasting in France, to develop a tool, a module of that model that accounts for grooming and snowmaking, which means that not only in terms of the physics, we account for the impact of grooming and we account for the physical properties of machine-made snow, which is a bit different than natural snowflakes, but also in terms of the practices of the ski resorts. The model accounts for the thresholds and the decisions that are mostly used in ski resorts in terms of how frequently the grooming takes place and which are the thresholds and which are the practices that are used for snowmaking in terms of temperature threshold, or in terms of also water amounts which are available for snowmaking and which are predetermined for running the model. And that is consistent with the practices in ski resorts. We can come back to it if you have questions. So that is the tool that we use as an impact model in a way to convert and to compute the evolution of snow conditions in ski resorts with and without snowmaking, with and without snow grooming, under past and future climate scenarios. So if you look at the next slide. So we used EURO-CORDEX data for future climate change and also historical scenarios. We used the 12 kilometers projections similar to the previous talk, and we used the EURA 5.5 kilometer reanalysis as a reference data set, as a reference observation data set, so to say, to statistically adjust EURO-CORDEX data in order to then drive the Crocus model with and without snowmaking for a number of locations across Europe. So here is a map of Europe where you can see the overlay of the EURO-CORDEX and the EURA reanalysis. So you can see that all of Europe is covered, including the islands to the west of Portugal and Spain, with a few exceptions. And also we're missing a few areas, although quite interesting, but unfortunately we missed them in the easternmost part of Turkey. But otherwise, even including Iceland, all of Europe is covered by this work. And the way we worked is we worked over not 3 areas, which correspond to a number of geographical units and administrative units across Europe. So in France, that would be département, or in Switzerland, cantons. And so we use these not 3 subnational, subregional administrative areas, so that in the future, it will be possible to compare the results from our work with socioeconomic indicators driving further applications of that data set. So if you go to the next slide. So again, we worked with those not 3 areas, not 3 regions, by steps of 100 meters on flat terrain. So we selected a number of EURA 5.5 kilometer reanalysis corresponding to each of those nuts by 100 meters elevation ranges. So it's a bit of a conceptual approach to map a reasonable number of locations to be handled, but maintaining some representation of the elevation dependency of the trends, which is critical for the issues that we are looking for. And so we identified mountain nuts on a case-by-case basis using a number of indicators in terms of altitude range, and where ski resorts are located. So you can see here all the orange nut-free areas correspond to mountain or to mountainous areas, and the green ones correspond to those low-lying elevations. So we processed also the low-lying elevations with only one elevation per nuts, and we use the average elevation. But for the mountainous one, we use several slices of elevation by steps of 100 meters elevations. So if you could next slide. So we used this work took place I think back in 2017, 2018. So we used the data that were available at that time, and we also used a number of EURO-CORDEX scenarios that were compliant and consistent with other Copernicus Climate Change Services SIS developments, in particular the energy ones. And so we altogether selected 9 GCM-RCM pairs for RCP 4.5 and 8.5, and 2 for RCP 2.6. So based on investigations and interactions with ski tourism industry representatives, including consulting companies, and also including discussions with ski resort managers that were used as pilot studies through this contract, we selected 39 annual scale indicators that refer to the snow cover duration, the beginning, the end of season, the peak SWE for natural snow or for groomed snow and managed snow, the temperature, snowmaking hours, that is how many hours in a given time period, especially in November, December, where most of the snowmaking takes place, what is the number of hours where the temperature is sufficiently low, and the amount of precipitation. So that the data set is not only used and not only usable for snowmaking and for ski tourism assessments, but it's actually a much broader ranging data set that can be used also for other applications, because data is also provided for natural snow across these mountain areas. So think of ecosystems, think of water resources, think of glacier. All of those applications can actually be approached using this data set, and it would be quite interesting to see that developing in the next years. So we didn't only provide annual values, but also aggregated indices over 20 years time periods, and not only the mean and standard deviation, but also the quantiles, especially the quantiles of 10%, 20% of the multi-annual values for each model pairs and for each RCP. The motivation for that is that when it comes to ski tourism and to snow, what matters a lot is the internal variability. So we know that winters are different from one to the next. You know that if you live in the mountains or if you go for holidays. And when it comes to the impact of climate change on ski tourism, the change in the mean is quite irrelevant, actually. If you're a ski resort manager, it doesn't matter much if on average there is enough snow. What matters is how often the conditions are sufficiently bad that it's actually a challenging years for your operation. So working with quantiles and working with threshold exceedance frequencies is way more relevant for those applications than looking at the change in the mean. And I think that is appropriate for a number of other climate change indicators. Do not focus on the mean, because the mean actually doesn't tell you much about the change. The changes the most relevant changes is how often the conditions are detrimental, or how often the conditions are challenging for a given activity. And this works, of course, we think of the extremes of precipitation, of the wind or the temperature for heat waves, but this actually works also for the lows, extreme highs, but also extreme lows when it comes to the snow cover. So basically, a snow drought or a winter with snow poor conditions is also to be seen as a climate extreme to some extent, and the frequency and the magnitude of those low-end snow extremes is really what matters the most for ski tourism. So if you go to the next point, you have an example of what we produced. This is for Upper Carinthia in Austria for 1,500 meters elevation. And this plot shows the number of days with more than 30 centimeters of snow on the ground. And we start by natural snow. And you see here in black the thick black line, this is the result from the reanalysis for this particular point, and all the thinner lines correspond to the historical GCM, RCM, which have been adjusted prior to running the crocus model with natural snow conditions. And now if you go to the next slide, you will see what we find for the projection under RCP 2.6, and then we add next one RCP 4.5, and then we add next one RCP 8.5. And what you see here is, of course, we see the trends for those different scenarios, but we see really changes in the frequency of occurrences of number of days. If you think is particularly on the reddish lines for RCP 8.5, how often we go below a given threshold, say 50 days or 40 days, and really it's the frequency of how often these conditions are encountered that matters the most for ski tourism. This is for natural snow, and if you go to the next one, you see what we find for managed snow. That includes snowmaking and grooming. Of course, grooming, we can study the impact of grooming, but snowmaking only occurs when there is grooming as well. It never happens that snowmaking takes place without any grooming. So this is the change for the past for managed snow, so including grooming, and you can see that the variability is much lower than with natural snow, and that is the effect of grooming and snowmaking, of course, and that is the purpose of those techniques. That is for the past, and then if you go once again to the different slides, you see the impact on 2.6, and then the change for 4.5, and then 8.5, and then you see that the trend is going to lower values for RCP 8.5, but you can see that with snowmaking and with grooming, with managed snow, the drop is delayed in time, and we do not encounter such low values as with natural snow at this elevation for the next decades. So it gives you a sense of how relevant that is to take into account snowmaking and grooming when you think of the impact of climate change on ski tourism. And if you only focus on natural snow, it's basically irrelevant for this industry. It's like, as a colleague from the US says, or from Canada says, it's like accounting for studying the impact of climate change on agriculture without accounting for irrigation. That is totally irrelevant. And that's the same here for ski tourism. You have to account for snowmaking and grooming if you need to provide industry relevant indicators for that particular sector. So if you go to the next slide, this shows an example of the indicators and the aggregation of the indicators across time over those 20 years time periods. So if you go to the next ones, you'll see examples of what we say for those different time periods. And we aggregate data for 2021, 2040, 2041, 2060, and 2081, 2100 without thinking of it. I mean, we thought about those numbers, of course, but it seems that these are time slices which have actually been used by a number of other publications since then, and including being reported in IPCC. So if you go to the next slide, this is how it looks like on the Copernicus climate change service climate data store. The data has been available since August 2020. So now all the data is available, and there is also a documentation about this data set. And if you go to the next slide, you'll see the example of variables which are available. So again, 39 indicators, either for the annual values or for 20 years aggregations of the data. And if you go next slide. Yeah, there is also an app that has been designed through the contract with Copernicus, and that has now been ported into the CDS. So the app directly draws on the data on the CDS, and you can navigate through this app. If you go to the next slide, you can navigate through the data set by choosing different indicators, different thresholds for those indicators, and different snow management configuration. Here you can choose between natural snow, groomed snow, or managed snow that includes snowmaking. And you have different time periods, different time horizons, different statistical indicators, the mean, standard deviation, or the quantiles, different elevations, and you can also compare on click between different regions. So that's displayed on the next slide, where you can actually select different regions across Europe. And on the right-hand side, a panel will appear to compare the values for those different regions for different elevations. And that is something that none of the data available so far for these ski tourism applications was provided. Many of the studies that have been available so far are focused on one particular country or maybe a couple of countries, and the pan-European assessments so far have only used natural snow conditions. So it's something that is not directly relevant to ski tourism industry when it comes to the long-term impact of climate change. So this is something that is available now that complements other sources of information at the local scale. So if you go to the next slide. Yes, in conclusion, so we provided a new European-wide set of climate change impact indicators for addressing the impact of climate change on mountain tourism, and in particular ski tourism. And as I said, this data set accounts consistently for natural and managed snow conditions, and we provide the water requirements that correspond to the amount of snow that is produced. So this can be used in water applications focusing on water resources. And as I said, I strongly believe that this data set can also be used for addressing a number of other sectors or a number of other applications in mountainous areas, because we provide indicators that are not only relevant for ski tourism, but also for a number of other applications. So I didn't go into much details, but our data set confirms that we project a major decline in snow reliability in European mountains. But this depends a lot on the horizon, on the elevation, and on the scenario, especially after the turn of the 21st century, at the end for the second half of the 21st century. And it depends a lot on the snow management configuration. As I shown, the results are quite different when we account for snow management or not. The data is available on the CDS along with the app. So here are the two links to link to the data set and to link to the software, to the app. The app has been available since, I think, December 29th, 2020. And this was tested through several case studies. So we have a number of examples where this data set has been used as a case study in Turkey, in Andorra, in Switzerland, and also now we know that some SMEs are using this data set to provide some services to ski resorts across Europe that are asking questions about the impact of climate change on their activities, and which are thinking about diversification of activities, or in terms of the impact and the adaptation strategy that they have to think of in the face of climate change. And I want to stress also that there exist higher resolution studies accounting for fine-scale topography and ski resort characteristics in more detail. Of course, this couldn't be possible to develop at the pan-European scale, so we really have to see it's quite complementary to have this pan-European approach available throughout all of European mountains on flat terrain by step of 100 meters elevation, and of course higher resolution data is available in some countries, but there are countries where the Copernicus climate change data set is filling a gap and is basically providing data where none were available before. So the next slide is my last slide. I just want to say that if you want more information, of course, there is information on the CDS with where there is a documentation about the project and about the data set, and there is an upcoming publication in Climate Services. These are the proofs. So I expect that the data and the paper will be published within a few days or weeks now. But this is really providing a summary of all of this work and describing different use cases of this data set, and which are the limitations of this data set, which also need to be accounted for. So I thank you very much for your attention, and I'm fully happy to answer questions you may have. Thank you.